Welcome everyone. Thank you for coming. This is our first time at Unreal Fest. We're really excited to be here in Seattle today to talk about how we use Unreal Engine at Rivian. I can't tell you how many times we've heard, what is a car company doing with Unreal Engine? They don't make video games. We're here to shed some light on that. So, my name is Eddie Reyes. I'm a senior manager at Rivian. I'm joined today by Raven Kay, lead designer, Raymond Chow, lead tech artist, and Kartik Mekala, lead software engineering. And of course, we didn't pull any of this off alone. We're representing for multiple teams at Rivian across design and engineering. And it took an army of talented and dedicated individuals to pull this together. So thank you for everyone on the team. Today, we're going to talk about how we use Unreal Engine at Rivian and why. Dive into the creative journey behind our latest art direction. Share some insights into our software development process. And if we have some time left over, we're happy to take some questions. So what are we using Unreal Engine for? We currently deploy Unreal Engine in every vehicle at Rivian. 5 reasons why we use it. Number 1, we're in the business of creating user experiences, not game engines. Our top priority is to continually improve the user experience. And that means we need to focus our developer time on the user experience over low-level graphics or reinventing yet another renderer. Number 2, Unreal Engine scales down, which is critical for infotainment, where computational efficiency is everything. Our hardware is running dozens of concurrent workloads at all times, and we need to share resources across all of those. Number 3, tooling. Unreal Engine Editor gives us a common platform for engineers and designers to come together seamlessly. Design iterations happen, and these tools empower us to embrace iteration without losing velocity. Number 4, developer and artist ecosystem. Hiring top talent is incredibly difficult, especially in automotive where real-time rendering in 3D is only now starting to take off. Unreal Engine has an amazing ecosystem around it, and it's growing. Number 5, Epic Games is an amazing partner. They've taken our requirements seriously, and they deliver every time, and shout out to the Epic Games HMI team. This is our infotainment module. It's based on a Qualcomm platform, and on R1, we render to 3 displays: the driver display, the center display, and the rear center display. It's the central access point to just about every feature in the vehicle, from navigation, radio, media, phone, various vehicle settings, and we even have a camp app. And the list of features is only going to grow over time. On the driver display, Unreal Engine is front and center. It plays a critical role in informing the driver of the vehicle's situational awareness, visually providing sensor data at all times, from low-speed maneuvering like parking and the associated parking sensors, to highway driving use cases like assisted cruise control and highway assist. On the center display, we've just recently deployed Unreal Engine across various apps, with real-time visualizations across the board, replacing tons of legacy still renders, which came with scalability challenges, as you can imagine, since we support every color, every trim, and every wheel package. In this photo, we see a Drive Modes app running on the center display. Depending on the motor variant, we have up to 9 drive modes. For on-road, we have all-purpose, sport, conserve, and snow. For off-road, it's all-terrain, drift, rally, rock crawl, and soft sand. Our team supports every single Rivian vehicle from R1 products to EDV. And of course, we're bringing Unreal Engine along for the ride in the upcoming mid-size lineup with R2 and R3. Some more about our ADAS, or Advanced Driver Assistance System visualizations. With Gen 2 launching earlier this year, we introduced Lane Change on Command, where we visually inform you while the vehicle automatically changes lanes with the turn of a signal. On the right side of the screen, from top to bottom, we render for blind spot monitoring, lane departure warning, manual park assist, and forward collision warning, among others. And we support a very similar set of driver assistance-focused visualizations on EDV as well. Recently, we've taken our art direction in a completely different direction from traditional photoreal rendering. And this was a bold decision, and we're proud of what we've accomplished. I'd like to hand it off to Raven Kay to walk you through that creative journey.
Okay. Thanks, Eddie. Hi, everybody. I'm Raven, lead visualization designer at Rivian, and I'm going to speak a bit more about our new cel-shaded look from concepting to production, mostly focusing on the drive modes application. All right, so here you can see the progression of our display art, starting with our early adoption of a 2D, more photoreal looking static images approach. Now we've shifted into just a completely real-time rendered, fully CG scene for all of our drive modes. And this approach started back in 2022 when we asked ourselves, rather than the industry standard of photoreal visuals, what if we instead created an illustrative style unique to Rivian? And we wanted this style to be reflective of our brand, so something bold, playful, and ambitious. But what would that actually look like, and how could we achieve it? Once we knew photorealism wasn't what our goal was, it was time for us to start pulling some inspiration. So on this slide, you can see some early references, really leading into more of a cartoony vibe, but specifically focusing on the Studio Ghibli aesthetic. And this was for a few reasons. First, their films celebrate the environment and nature, which was directly in line with Rivian's commitment to sustainability. Also, their characters and narratives evoke a strong emotional response, which is what we wanted for our drive modes application. And lastly, their distinctive art style would set Rivian apart from other tech-focused interfaces, creating something that's more appealing to customers looking for a unique experience. So now that we had a little bit more of an idea of an art direction, it was time to take it a little further. Now you can see some early illustrative explorations of merging this cel-shaded cartoony look with more of a technical line art style. And we liked how this was coming together, so we dove a little deeper. Here you can see taking this style and treating it to other elements in what would be our drive modes worlds. Things like foliage, the ground, the sky, and the sun were all thought about in this style. And now that we had all these pieces, we had to put them together into actual illustrations of these drive modes in the worlds that they could possibly be in. So you'll see this over the next few slides. So the worlds were very important, but so was the car. As you can see here, there were multiple views for our vehicle, so we knew even with drive modes, it would be seen in multiple perspectives, but also across other applications in our infotainment system. So we were paying attention to things like highlights, shadows, and reflections, as well as line weight for the actual cel-shaded style. On top of that, we have multiple different exterior paint options. So this was really important to consider in the beginning while trying to create our environments and the color palette. We wanted to make sure that our drive mode scenes and settings helped support the car. It didn't compete with it. So the car always needed to remain a focal point in all of our drive modes. So we now had a really nice artistic idea, right, going forward with 2D concepts, but we still had no idea how this actually would translate in a CG world. Would some of it fall short? Would some of it not look correct on our driver displays? We still weren't sure, so we had to move into production. Again, I'm going to focus specifically on our worlds and our set dressing and all the assets inside of it, mostly for drive modes. So here are some additional concepts for our drive modes, thinking specifically about Unreal Engine and framing. Again, we wanted to find ways to communicate to our customers what each drive mode experience should feel like. So it was important that the sets and the props and even the camera itself all be indicative of the feeling once you get into that drive mode. On the right, you can see an early first passes of some previs of these concepts in Engine. And while the concepts on the left ended up being a bit more detailed, you'll notice as I continue on that some props, environments, and cameras were actually kept. And this is all great. Now we have actual framing and sets and everything for our drive modes. But something else to consider is switching between drive modes, right? So for example, a customer might be in all-purpose mode, but want to switch into conserve. What would that look like? So we had to explore that too. So here's an early animation of what some of this could potentially be, what could be displayed on the screen while switching drive modes. So here you can see a first pass of the car itself moving into the different environments, followed by a secondary concept of the environment and the camera itself changing around a stationary car. And we thought this was really fun and playful and ambitious, hitting some of our original goals. So we went forward with this idea. And this is an early first pass inside of the engine, combining all of these concepts together. So you'll notice some experiments in the treatment of the environment props, camera angles, the sets, and all of this was created by multiple artists. So because there were so many drive modes, we decided to kind of tackle this together as a team, but also independently. So all of these 2D elements, 3D models, shaders, effects, animations, and the renders were all handled start to finish independently by different artists. And we just kind of pooled together what may or may not have worked as a collaborative effort. And it's a lot to go through. Honestly, there's a lot of assets. But you can see here our final of where we landed. Again, you'll notice some props, environments, and cameras that we kept. So our early previs was super important in order to help our workflow just run smoothly and get to this point. But again, we had a lot of drive modes and a lot of artists working individually. So we needed to make sure in the end that all of our drive modes and art assets looked cohesive. In order to do this, we decided to focus on one specific mode for the polish overall, and that ended up being our camp mode. You can see on the left, again, more of that early 2D photoreal style, and then where it's landed now. And we thought camp mode would really be the best scene to try and polish and hone in because it kind of reflected back to that idea of a Studio Ghibli inviting, warm, welcoming feeling. So in this mode specifically, we could play around a little bit more with some ambient animated assets, as well as time of day, and also how to treat that. So how could we show the passage of time, as well as depth cues, and still line art in the cel-shaded style without using traditional artistic methods like directional lights or height fog? And the answer really just became color. Not just that, but we had to explore how to handle the line weight around different assets in order to make sure your eye goes towards the car. And here's a sneak peek behind the scenes for how that level was created. Like with most standard CG scenes, you'll see there's a camera, so everything around the car is all going to be in frame. You'll also notice a mix of 3D elements and then these cards with 2D art on them. And this became our approach for all of our drive mode scenes. It's for a few reasons, actually. The first, just artistically, we could get a little bit more control this way, especially when it came to depth cues for the lines themselves. It also helped troubleshoot and problem solve some technical issues that we ran into, because from the beginning, we always knew that our art assets and everything in drive modes would need to be as efficient as possible. Because of software sharing, it was never going to just be about the drive modes application itself. There were multiple other applications that would need to run at the same time. And all of this was made smooth and efficient as a process because of our close collaboration with the dev team from the beginning. So our design team and devs from the start worked side by side to hit both the artistic direction and also the technical requirements to make this possible. I'm extremely proud of everything that we've done. And on that note, I'll hand it over to Raymond to speak more about the vehicle and the technical art approaches.
Awesome, thanks Raven.
Yeah.
So hi, my name is Raymond, and today I want to talk about some tech art challenges we face in tech art and how we overcame them. As you can see here, this is one of our North Star references image in 2D. And deconstructing the cel shading art cell, we have 3 clearly defined color tones, some stylistic lighting and reflections, and finally there are hard shadows with clean edges that also need to be dynamic for the drive modes app. We decided early on that it would be difficult to achieve the same look in 3D using a realistic lighting model. So we opted instead to not use lights and do everything with unlit shaders. Additionally, meshes were UV'd in a way to minimize the use of textures. This type of hyper-optimization allowed us to free up memory and resources to other applications across the infotainment platform. In this example here, for the lenses, Everything here on this top left in the shader, we could specify all those islands to be black, while all the UV islands for the light bar below, for example, would be shaded red. Shadows, we're done with decals. For the vehicle, the decal was attached to the blueprint so that whenever the vehicle pose changed or the environment morphed, the shadows will still stay intact. Color space was another interesting issue. Because our North Star images were done in Figma, and Figma only supports sRGB values from 0 to 255, and Unreal uses linear color space. So we needed to figure out a way how to do a color conversion, which will allow for quick input and iteration. Our solution was to create a post-process material to replace the tone mapper. And we took the final color buffer and raised the color values by 1 divided by 2.2, converting the linear colors to sRGB. The end result allowed us to quickly iterate from specs given to us by designers and input them directly into the engine. One quick note on this is I did attend the color session yesterday from Rod Bogart, and I think this actually should be color encoding in that color space. Excellent talk. If you haven't seen it, highly recommend watching it later on YouTube if it's available. And moving forward, we would definitely reevaluate our color pipeline. Vehicle lines were another important aspect of our cel shading lifestyle, cel shading art style. As you can see, each category has its own line weight and thickness. And for the vehicle, we use two solutions. For the inner lines, we use geometry, where we can model the lines and thickness, as well as tapers. This helped with side shots with grazing angles, such as conserve, and also allowed us to cover any gaps in the models, such as spaces between the doors. For the outlines, we did a post-process material and screen space. This way, our outlines could work in any angle for the vehicle. We implemented edge detection algorithm using depth buffer. And additionally, we also used a custom depth buffer, so objects in front of the vehicle would correctly occlude the outline. For the instrument cluster, we had to do additional refinement due to the smaller display. Oftentimes, these lines were a single pixel thick. To combat this, we reduced line contrast and strategically removed any lines causing the vehicle to look cluttered. In certain areas, geometry lines were also replaced with sign distance field textures to help with the aliasing. As you can see on the right, overall this gave the R1 a much cleaner look. Reflections are one of the most challenging aspects in this project, mostly because we didn't have any lights or reflection captures in our scenes. Not only did we aim to have dynamic reflections, but we also wanted the ability to have unique reflections for each drive mode. Again, we turned to sign distance field textures. On the left is an example of a hand-drawn reflection in UV space, and the right is the converted sign distance field version. The gradient in a sign distance field texture allowed us to morph reflections from drive mode to drive mode. In this example here, we start with an off third drive mode reflection for snow. And during the transition, if our current camera position is less than a given threshold value, we lerp to a calculated reflection before settling in to a new auto reflection for drift. As you can see, it adds a ton of life to the scene and really ties the vehicle to the environment. What's nice about this system is that because the Drive Mode app allows users to two-finger touch to orbit the camera view, using this technique allowed us to create a more immersive scene by having the reflections subtly react to the user's input. I also really want to quickly touch base on maintainability. Given the number of different vehicle configs and variants there are, using Unreal Engine saved us from having to maintain and render over 18,000 images just for the Drive Mode app alone. On the back end, we created a configuration component that leveraged material parameter collections and data tables. This reduced the need of having to create multiple material instances or incurring the overhead cost of a dynamic material instance. So for example, if you want to change the body color from the body config component, this would trigger a data table lookup for the new color values, and that in return is fed into a material parameter collection in the shader. Adding new colors can simply be done by adding a new data table row. Next, I want to talk about our scene transitions. We had a persistent sky so that color bands can lerp between drive modes and not have any visual pops or glitches. We also used a cube for the sky mesh so that the lines did not distort from any wide camera angle lenses. The sun and moon were also persistent, and would rise and set to mimic the passage of time when animating to a new drive mode. If you recall earlier, the transition concept was to have the car remain in place but react to the scene as it changed around it. The challenge here was to figure out how we can unload the drive mode sublevels while still having smooth transitions. As you can see, our transitions always happen from screen left with the old scene rolling out and the new scene rolling in. By adding the changing vehicle pose and rotating wheels, it gives us the illusion of the R1 driving to a new terrain. Once the animation finishes, we unload the old sublevel. For environments, all objects were kept as static meshes, and animations were done through a vertex deformation in the shader. All objects in the scene were also given a drive mode index, so our environment manager can specify which objects should be transitioning in or out with a single alpha. For the props, we add additional shader logic so they can shrink or grow during transitions, while background cars can translate vertically. To help with continuity, we also add in additional grid that will roll in during transitions and be a mix of the old and new terrain colors. This provided a nice gradient as it transitioned through the scene, and also helped to hide any gaps in the terrain caused by the vertex deformations. And finally, it was always important to us that these animations never locked the user's ability to interact with the UI. If they so choose, they could always switch to a new drive mode, even in the middle of a transition. So we developed a transition manager to ensure that everything is seen, including camera, vehicle, sky, sun, and moon, environment, and props, would always stay in sync and still transition smoothly. Now I'll hand it over to Kartik for some engineering insights.
Thanks, Raymond. Hey, I'm Kartik. I'm here to talk to you guys about our development process and how we've architected our software, and hopefully give you guys some insights into what it's like to work in our team. I'll start with some high-level goals. At the end of the day, we do make automotive software, so it's really important for us to really hold a high bar in terms of system stability. And as my previous speakers have mentioned, we do share our system resources with a lot of different applications within our entertainment system. So like hyper-optimizing your solutions tend to be a recurring theme in our day-to-day. At the same time, we want to be able to really enable the high level of creativity that comes from our design team. And to be able to do this, we borrow from the game industry, right? So we wanted to design a process that enables fast iteration and tight collaboration with the design and between the design and the dev teams, and really make all of this possible. So this is what a typical workflow process for any new feature looks like. We usually start with like a high-level requirement from the design team, and the design team usually consults with the engineering team to just make sure that any system constraints are taken into account before the actual requirements are handed to the engineering team. And once we have that, we jump straight into prototyping the feature within the editor. And we've invested in some processes and some tools and infrastructure to make that possible, and I'll cover that in just a little bit. And once we have that early prototype within the editor, the design team and the engineering team are able to have that tight collaboration. It's very often that we find our designers and engineers jumping onto a Zoom call or like getting into a room and really playing with things within the editor, authoring, vehicle poses, cameras, and then committing that pretty quickly as part of this tight collaboration process. Once we have that, once our ambitious design team is happy and the engineering team is happy with that initial prototype, the engineering team usually breaks off and really hardens that solution for system stability and for that hyper-optimized performance. And to do this, our engineers have their dev kits at home, and they are able to do some amount of end-to-end hardware testing. But once they're happy with it, the software is handed over to our vehicle integration team. And these guys do an amazing job to be able to test that software within the vehicle and give us feedback in both usability, stability, and performance, and all of that. And then once we're able to incorporate all of that feedback from the integration team, we submit these changes into our production source control. But once we've done that, the software gets deployed to a much larger fleet of dev vehicles within Rivian. And we get a lot more feedback from the larger Rivian team, our key stakeholders. And once we've incorporated all that feedback, gain that confidence through mileage accumulation, through all of our testing, and once everyone's happy with it, there's a sign-off, and it gets actually released into the next over-the-air update for our customer. Here are some examples and ways in which we really try to sink into that fast iteration and tight collaboration with the design pieces. Here's a video of just a debug menu that we use within the editor. And what this allows us to do is simulate the exact same signals that we expect to see in an actual vehicle. And you can see how this is really powerful to create that first prototype without having to get near a Rivian vehicle and do all this within the editor. And at the same time, it also helps engineers sort of debug, optimize their solutions. And like I said, also collaborate with the design team and really author and tweak things to what we think is perfection. Another workflow that we heavily use, we have the ability to actually record vehicle signal data from our vehicles and actually play it back into our editor. So this video is actually captured just from within the editor, and we just have a process that's playing back that, what we call PCAP data into our editor. And you can see how this is powerful, both in terms of the engineering team being able to debug issues that are reported by the test team, but at the same time also iterate with the design team. We often will make changes to the user experience and iterate through it within the editor and know that a similar user experience is actually is what we expect when the software is put into an actual vehicle. Another example here, like our designers and our engineers have the ability to just use this debug menu, play with the vehicle pose. This is an example of the vehicle pose and the camera tuning, but we do sort of similar tools in other places. Really tweak it to their satisfaction, and then with the hit of a button, commit that into the software and know that that's what they can expect to see when it's actually dropped into a vehicle. I'll switch gears on you guys a little bit here because I'd also like to give you guys some insight in just the way we've architected our software. Again, I'm going to repeat myself a little bit here, but we share our system resources with a lot of different applications that are within the infotainment system. We are rendering to 3 screens, but even if you consider just a single screen, the instrument cluster, there's just a lot going on. We have the navigation view on the left, we have the camera view on the right, we have the 3D ADAS view in the center, and that's the piece where our Unreal Engine application is rendering into. And there's a lot of additional 2D UI, some of which is like mission critical for driver aid. And to be able to do this presents some additional challenges that are not typical in the game development processes, right? So being able to elegantly compose all those views together and figure out a good way in which we can optimize and share these resources across our different applications, that's a challenge that we sort of deal with on a day-to-day. Two other requirements I wanted to mention here. We do support driver safety and driver assistive features like blind spot monitoring, forward collision warning, manual park assist, just to name a few. And it's really important for us that once we get these signals from our vehicle, we show that information to the driver as soon as we possibly can. So that's that low latency piece. Also, like I mentioned, we try to hold ourselves to a really high bar in terms of system stability. But in the rare cases that, for example, the 3D view did crash or go down, then we have additional fallbacks in place, right? And the way we've designed our system is to ensure that, for one, the other views within the instrument cluster are not affected when something goes wrong within the engine. And at the same time, we have some fallback mechanisms of just preserving as much vehicle functionality as we possibly can when things do go wrong. So to pull this off, we worked with our amazing partners in the Epic Games HMI team. We do use the Android single instance as a service plugin provided to us within the engine, and Joe talked about it a little bit in one of the prior talks in the session, so do please check it out. And the way we use that, we have the instrument cluster app and the Unreal Instance service. Both these are separate processes that run within the vehicle. The instrument cluster app hosts that 3D ADAS view, and that's one of many views, like I had mentioned. And it's able to send that view render surface across to the Unreal instance. And that's where the Unreal Engine application is hosted and is able to render into that render surface. And we also have bidirectional communication between the app and the service by means of callbacks, like when, for example, like a level is loaded or a level is unloaded, that sort of callbacks. And we also have the ability to send data from the application into the service. And also what calling out here is that both the app and the service have their own communication channels to the vehicle signal service. And that sort of assists in that process isolation piece that I'd mentioned earlier. Again, in the odd cases where something goes wrong, we have fallbacks in place. If the app goes down, it almost instantly boots back up because it tends to be a really lightweight application by itself. And we don't need to reboot the Unreal Engine service or the Unreal Engine application. And if the Unreal Engine app does go down or the service goes down, the remaining views within the instrument cluster applications are not affected by it, and a lot of the vehicle functionality is still preserved. So that was the instrument cluster. When we decided to integrate this into our center console, that presented some additional requirements or challenges. We did want to integrate real-time 3D into multiple applications within our center console, and that includes the drive modes, the camp app, the energy app, and the settings app today. And what we wanted to make sure is when you're switching between these applications, there's like a seamless user experience. So we don't want like a loading screen or any of that. But we wanted the real-time 3D to be available to our drivers and our users as soon as possible. And we also wanted to make sure that the amount of system resources or just the developer complexity required to introduce real-time 3D into an additional application is as low as we could possibly design it to be. So to pull this off, we leaned on our amazing Android single instance plugin again, and we were able to extend it to essentially work with multiple applications. We still have the single Unreal instance service that's hosting all of these center console content. And then we have multiple applications providing that 3D view for the Unreal Engine application to be able to render into. And the app and the service are able to maintain context in a way that the user is able to switch back and forth between applications and preserve context when they're switching between applications. And also just the ability to add another real-time 3D application in one of our apps is pretty low in terms of, again, like I mentioned, the system resources and just the developer complexity of introducing more use cases. So one of the things we also wanted to do was all this amazing cel-shaded content that we created. We were always looking for ways in which we could give that same impact, that same brand recognition into other use cases within Rivian. And the way we did that was using Unreal Engine plugins. So what we were able to do is create a plugin with all our shared core like assets and services, and use that plugin inside an infotainment module that helped us deliver those driver display and center console use cases that you guys just saw. But at the same time, we were able to create like an image generation pipeline, and that allows us to generate images for all the different variants and vehicle configurations and the things that were mentioned earlier into our infotainment, our mobile app, our website, social media channels. And this also sets us up in a really good place to be able to consider additional use cases in the future. And that's something we're always thinking about, is just how we can add additional brand recognition and real-time 3D impact for Rivian. Here's how we were able to celebrate that cell shading look. Like I mentioned, we were able to bring it into our mobile application, our website, our social media, and I thought this was fun, the NASDAQ announcement in Times Square, New York. That was me. I'll invite Eddie back to the stage to close us up on some final thoughts.
Great. Thanks, Artik. Cool. We're really excited about the future of Unreal Engine and automotive and the impact that Rivian has had here. And we'll have more updates rolling out every month. In fact, here's an update that we just pushed out a few days ago. For R1 owners in the audience today, every time you make a change in your drive mode settings, we visually explain exactly what you changed and the intended side effects across ride height, ride feel, regen, and stability. This update is rolling out right now with software version 2024.35. We're also excited to announce that we'll be adding 6 additional vehicle classifications within the ADAS view on our Gen 2 vehicles. ADAS team has been hard at work adding support for pickups, sedans, SUVs, buses, minivans, and delivery vans, expanding on a previous set, which was cars, trucks, motorcycles, bicyclists, and pedestrians. This is a direct result of Rivian's modern machine learning first autonomy platform, which uses early fusion of the vehicle's cameras and radars to generate a 360-degree surrounding of the scene. There's tons more to come, so stay tuned for future over-the-air updates. And thank you for coming. We'll go ahead and open up for Q&A. And also, we're hiring. Please come talk to us outside if you're interested in careers at Rivian.